All right, welcome back and welcome to the last class of this course, which is on multivariate analysis and control charts. All right, to get started, let me try to give you a couple of examples to motivate as to why we need multivariate control charts, and then we'll look at some control chart examples. To start off, and just a quick review, so far we have really done is univariate control charts. We had single quality characteristic, and then we plotted a single control chart. But in many real world applications and in many scenarios, you would actually see that there are more than one quality characteristics. In fact, this is an example that I'm showing here on the right-hand side. Imagine measuring the quality of some type of a structural component. Then we are not just measuring one quality characteristic, let's say hardness or Vickers hardness, but we're also measuring fracture toughness and a bunch of other quality characteristics. So really, in many practical examples, we have to monitor more than one quality characteristics. Okay. Another example is think about the water that you are drinking. Water needs to have certain mineral content, certain vitamins, or maybe not vitamins, but even within mineral content, you have more than one elements that needs to be present in the water. And then there are a bunch of other examples where you actually see that quality control is more than one. Now, technically, you can do a single control chart for every single quality characteristic, but it is not a good idea. And I want to show you first why it's not a good idea. All right, so first thing is, let's actually look at the plot on the top right side. On the top right side, the figure that you see, there is some type of a relationship between hardness and toughness. They are not completely independent of each other. And now when quality characteristics are dependent on each other, we have to be very careful when we draw the control charts. And I'll show you an example. I have taken this ball bearing and I have the inner diameter of the ball bearing, which is called the bore, and then the outside diameter of the ball bearing. And then I'm basically doing a control chart for outside diameter and then the inside diameter. So this is your outside diameter. And then this is the inside diameter. Now, if you visually look at these two control charts, again, two quality characteristics, two individual control charts, you might not see anything wrong. In fact, both of them would look pretty much in control. Right? Now, if both of them look in control, what is the wrong? What are we missing here? Now, it might not be immediately clear what are we missing here. Let me try to show you slightly differently. Let's observe the first control chart and the second control chart together. You see, when the first control chart is going up in the beginning, the second control chart is also going up. When it is going down, the second control chart is also going down. Similarly, when the first one is going up, the second one also goes up. But right around the middle, where I have this red arrow, you see that when the first control chart is going down, the second control chart is going up. When the first control chart is going up, the second one is going down. When the first one goes down, the second one goes up, and so on and so forth. So what we see here is really the first control chart and the second control chart are actually positively correlated before. So if I were to just do this partition here, then before this partition, they are positively correlated And then after this, they are negatively correlated. And this idea of positive and negative correlation is very much clear if you do a scatter plot. So what I've done here is I have taken the first half and the second half, and then I've just simply done a scatter plot. So this first half of the data point, which is positively correlated, which is shown in this area, and then the negatively correlated region is in this area. So you see, there is a transition in the correlation structure of the data, but if you plot single univariate control charts, you're not able to capture that. So what I'm going to say here is that multiple univariate control charts do not capture the correlation behavior. Right? Correlation behavior between, you can say, quality characteristics. Okay, all right. So this is one challenge with using multiple univariate control charts. And then this is what I'm summarizing in the first point here. Individual control charts fail to detect the correlation structure. But there's one more challenge. There's one more challenge with using multiple univariate control charts. And that challenge is either your type 1 error, which is alpha, or type 2 error, which is beta, could get inflated. And let's try to understand what this idea of inflation means. Consider two quality characteristics monitored by two XBAR charts, respectively. 3 sigma control limits are used in each control chart, and type 1 error probability of each chart is alpha equals to 0.0027. Let's say we're interested in detecting a mean shift of 2 sigma in the process mean. So if you look at the first scenario here, for each individual X chart, the out of control condition is when a sample point is outside of 3 sigma control limits. If this is the rule, which is a standard rule, your type 1 error is 0.0027, and then your type 2 error is 0.84. And then your ARL1 is 6.25, which is basically 1 over 1 minus beta. Now, if you look at rule number 2, if either one of X charts detects an out of control condition, then the whole system is out of control. Now, if we use the rule-based system that we discussed in chapter number 3 and 4, I think 3 a little bit, I guess, yeah, somewhere 3 or 4, you can actually use the rules to find out the type 1 and the type 2 error. Now, I'm not going through the calculations again, but I'm going to show you that type 1 error for this case is 0.0054, and type 2 error is 0.705, and then ARL1 is 3.33. Okay, now let's look at the last one, which is if both X chart detects an out of control condition, then the whole system is out of control. Now in this case, your type 1 error is 7.29, 10 raised to the power negative 6, and 0.974 is your type 2 error, and your ARL1 is roughly 40. Okay, so now you see something going on here. You see, when we're using an individual control chart in part A, where you have just one quality characteristic, you have type 1 error of 0.0027, type 2 error of 0.84. But if you use multiple control charts together, you could see an inflation in type 1 error, or you can see an inflation in type 2 error, right? And whenever there's an inflation in type 1 and type 2 error, it's not good for your control chart, because now you're essentially making the control charts worse, right? So this is sort of the second challenge with using multiple univariate control charts, which is either alpha or beta could get inflated. All right. So these two are the main challenges. Now you can, sometimes there are ways in which people adjust type 2 error and type 1 error, but usually, this is done by increasing the sample size. And then again, we have talked about this multiple times in the past that increasing the sample size is not a good idea because the sampling cost goes up, right? So it may not always be feasible to increase the sample size. And then this problem actually gets worse if you talk about having hundreds of quality characteristics. You can't even track hundreds of quality characteristics on a control chart. It's just very challenging. And this is the problem that we typically call as the curse of dimensionality, right? When you have lots of quality characteristics, it just becomes difficult to do any kind of an analysis. So this is where multivariate statistics come into picture. I'm going to spend some time telling you about multivariate statistics, and then we will develop the control chart. So really what we're saying in multivariate statistics is that your quality characteristic X is not a scalar anymore, it's a vector, right? And I'm going to use this notation of underbar to represent that it's a vector. So represents vector, okay? And what we're really saying is that this X is equal to X1, X2, X3, dot, 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 up to XP. And I'm putting a transpose here because this is a column vector really. Okay. So each X1, X2, X3 up to XP are individual quality characteristic. For example, let's say I'm saying that X under bar is the quality of water. If X under bar is the quality of water, then we can say that X1 is the concentration of maybe potassium. X2 is concentration of calcium. X3 is concentration of, magnesium or something like that, right? So each of these individual XS represent quality characteristics, and each of them, X1, X2, all of these are individual quality characteristics. So this follows a normal distribution with mean mu1, variance sigma 1 square. X2 follows normal with mean mu2, variance sigma 2 square, and so on and so forth. Okay. Now, just like a univariate normal distribution, we can define a multivariate normal distribution, which is X under bar, following a normal distribution with mean mu under bar and a covariance matrix sigma. This is your covariance. And now let's actually look at individually at X, mu, and sigma. So X is clear. X is your column vector, X1, X2, up to XP. Your mu under bar, this is equal to mu1, mu2, up to mu p. And then mu I or mu1 is the quality, not quality. I want to say this is the mean of first quality characteristic. And then so on and so forth, okay? Just dot, dot, dot. You also have another thing here, which is the sigma. Sigma matrix is basically sigma 1, 1, sigma 1, 2, up to sigma 1p, sigma 2, 1, sigma 2, 2, sigma 2p, and then dot, 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 you have sigma P1, sigma P2, sigma PP. Now, there is some structure to this matrix that you would want to keep in mind. The very first thing is that this diagonal the diagonal elements of this matrix are essentially the variances of ith quality characteristic. So what I'm really saying here is that sigma I is the variance of ith quality characteristic. Okay, so it's basically, you can essentially say that sigma I is equal to sigma I squared. Okay, good. Now you have sigma ij, which is actually equal to the covariance between, oh wow. Okay, let me try to fix this. Okay, so covariance between I and J, so ith and jth quality characteristic. Okay. We don't have to worry about how to computing them because for most part of this course, I will provide you these covariance matrices. All you have to do is to use them. But let me quickly give you the formula as well, so you have it handy. It's the expected value of xi minus mu I times xj minus, okay, something is wrong with my Apple Pencil, I think. It's behaving very weirdly. It's xj minus mu j. Right. Something that you should keep in mind is that xi and sigma ij is equal to sigma ji, which is basically saying that covariance matrix is symmetric. Yeah, something is wrong with my Apple Pencil today. Symmetric, right? So that's one property that you should keep in mind. Another thing that you should keep in mind is sigma I is not equal to 0, because this is really the variance. Variance cannot be 0. If variance is 0, it becomes a constant quality characteristic. And then sigma ij, this could be 0. And if sigma ij is 0, this means that ith and jth quality characteristics are uncorrelated. Okay, that is something that you should just try to remember. Now, we can compress all of this information into this notation that X follows a multivariate normal distribution with P dimensions, mean, mu under bar, variance, sigma. And then you can also write this actually. You can write down the corresponding PDF, which is f of x under bar. This is equal to 1 over square root of 2 pi raised to the power p, 1 over determinant of sigma matrix raised to the power half exponential exp negative 1 over 2 x under bar minus mu under bar transpose sigma inverse x under bar minus mu under bar. And then that gives you the PDF. This thing right here is the determinant. Determinant of sigma. Okay, And that's pretty much it. Now, one thing before we move on very quickly, it's very much like a normal distribution. In normal distribution, if you look at univariate normal distribution, it's like a bell-shaped curve. If you go to bivariate, where you have two quality characteristics, this bell shape essentially becomes a two-dimension, like a real bell, which you see on this figure right now. As you go to higher dimension, even higher dimension, let's say 3, 4, or 5, it is just not possible to visualize them. But we can do some visualization in bivariate quality characteristics, which basically you need 3 dimensions. The first dimension is your first quality characteristic. The second dimension is your second quality characteristic. And then the z-axis is showing you the PDF. Okay. Now, what I want you to see here is that there is a difference between the first one and the second one. The first one looks very symmetric and looks, if you take basically a projection of that, it looks like a circle, right? When it looks like a circle, what happens is sigma ij is 0, which means xi and xj are uncorrelated, okay, which we just saw. But on the other hand, if it is not symmetric, if it is stretched in some directions, for example, in this one, it's one of this PDF is stretched in one direction, right? And when this happens, they're either positively correlated or negatively correlated. In this case, if you see as x1 increases, x2 also increases. So this is showing positive correlation. And on the other hand, if it looks something like this, then you would say that this is negative correlation. All right. Great. Now let's move on to some sample statistics, because this is what we'll use to compute our control charts. So it's very much like what you've done in univariate control charts or univariate statistics. Let's say x under bar is x1, x2 up to xp. Then you can write down the corresponding mean of x under bar, which is x over bar under bar. This is nothing but x1 bar, x2 bar, all the way up to xp bar. Okay, where your xi bar is equal to 1 over n summation of xij, j is equal to 1 to n. And that's pretty much it, right? We've just put everything in a vector form. That's all we have done here, okay? So this is the sample average vector. And then the second one we're going to talk about is a sample covariance matrix. Sample covariance matrix. And then this is represented as uppercase S, which is 1 over m minus 1, summation of k is equal to 1 to m, x under bar k minus x over bar under bar times x under bar k minus x over bar under bar transpose. Right? These are your individual measurements. And this is your mean vector. Actually, I don't want to call it mean vector. This is the sample average. Sample average vector. And you can write it nicely also. You can just spread this out as S11, S12, up to S1P, S21, S22, up to S2P, up to all the way up to SPP, SP1, SP2, And then instead of doing the matrix calculation, you can in fact do just calculation of every single element, which is easier in some cases. SII, this is a sample variance of xi. So you can write this simply as 1 over m minus 1 summation of x ki minus xii, sorry, xi bar whole square. Summation goes from k equals to 1 to m. And then you can similarly compute Sij. This is equal to sample covariance of xi and xj. And then the formula for this is, let's do the formula. This is 1 over m minus 1. Now again, for exam purposes, you might not have to compute any of these because I will provide you. This is more like a sort of background that I want you to know because doing these things in exam is just very, very messy. Okay, so that's your sample covariance matrix. And then just like, we know that sample average follows a normal distribution. Sample average vector also follows a normal distribution with P quality characteristics, mean, mu under bar, and sample covariance and variance 1 over m sigma. Okay. All right. So this is where I will stop the first part. Next time when we meet, we'll talk about control charts, hypothesis testing, and we'll stop there. All right. Thank you.